Hi, I'm Whitney Espich, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
Welcome to MIT's Faculty Forum Online. I'm Deborah Blum, director of the MIT Knight Science Journalism Program and publisher of Undark Magazine, and I will serve as your moderator today. This broadcast is sponsored in part by the MIT Federal Credit Union and MIT Professional Education. A reminder from me that after we hear from today's guest, we'll field your questions for her. Please use the Q&A feature on your Zoom toolbar to ask them. We'll get to as many as time allows. Meet Noelle Celine. She is an associate professor in the Institute for Data, Systems, and Society and the Department of Earth, Atmospheric, and Planetary Sciences at MIT. This fall, the terrific MIT Press, the terrific was my addition to the script, published Celine's new book, Mercury Stories, Understanding Sustainability Through a Volatile Element. You can learn more about the book and our speakers on today's event site, which we'll post in the chat now. And Professor Celine will start with an overview of the book and discuss its reception to date. We're so happy to have you here, Professor Celine, and the stage is yours.
Well, thank you so much. And I hope you can all hear me. I apologize in advance if the internet cuts out. I've been having some minor issues here, but I'm really thrilled to be here for this faculty forum and to really engage in a conversation about mercury pollution and also about how mercury pollution can tell us things about broader issues of sustainability and how to ensure human well-being today and in the future. How can we learn from this millennial-long history of people and their interactions with this toxic but also fascinating substance. So I haven't been working on mercury for millennia, but I've been working on mercury pollution for nearly 2 decades now. And that work, much of it at MIT, is what motivated my new book. So to kick off the conversation, I'm going to spend about 15 minutes just giving you a brief introduction to the mercury issue. Tell you about why I think it's such a fascinating example about people's interactions with the environment and why I think it's a rich case to learn lessons about sustainability more broadly. So in my work at MIT, I study how mercury travels in the environment, the challenge of mercury pollution, where it comes from, where it goes, and the main tools that I use are models and data analysis. Mercury is a global pollutant that poses risks to human health and the environment. And it's emitted to the atmosphere and travels globally, and then builds up in toxic concentrations in part as methylmercury and poses risks to humans and the environment. The emission sources are its intentional use in products and industrial processes, in mining, such as today in artisanal and small-scale gold mining, but also as a byproduct of burning fossil fuels, primarily coal. So on the left-hand side of the slide, I'm showing a normalized graph of mercury concentrations as measured in the Arctic, in Arctic biota, as a fraction of present-day levels. And this kind of history, where you see a low level over time and then it shooting up right about industrialization, is typical pattern that you see in a lot of different environmental pollutants, including carbon dioxide. Back in 2002, about the time that I started working on mercury, the United Nations Environment Program conducted a global scale scientific assessment. And they found there was sufficient scientific evidence of adverse impacts on human health and the environment from environmental releases of mercury that global action was warranted to address these issues. And today, we have a global treaty on mercury called the Minamata Convention on Mercury, and that entered into force in 2017. The Minamata Convention was named for the town in Japan where health effects of methylmercury were first identified, and that pollution started in the 1950s. Mercury is illustrative of a broader set, though, of sustainability challenges. And one of my main thoughts as working on mercury is, isn't this related to a whole bunch of other things? For example, energy. Mercury is emitted from burning coal. That's one of the major sources of mercury pollution. So mercury really intertwined with energy futures and also the climate issue. The example of Minamata, mercury is very connected to human health. In Minamata, Japan, that's a picture of one of the affected people from Minamata. Methylmercury poisoning was first identified, has serious impacts on neurological systems. In the top right, thinking about livelihoods and supply chain kind of issues. Mercury is used in artisanal and small-scale gold mining, which provides income for tens of millions of miners and their families across the world in more than 70 countries in Asia, Africa, and Latin America. And this could be the biggest source of mercury pollution to the atmosphere globally, possibly exceeding coal burning. And on the right, this linked to food and fish and safe fish. We're concerned mostly, most people in the US and Europe, for example, are concerned about impacts of methylmercury at low levels. And for that reason, I'm showing dietary advice, and a lot of this dietary advice is geared towards pregnant women and children, advising people to eat fish low in mercury and avoid eating fish that are high in mercury, such as tuna or swordfish. And I'll talk about the health damages of mercury in the next slide. So, how serious are the health damages of mercury? In the early 2000s, it was estimated that more than 300,000 babies in the United States were born every year to women whose mercury levels exceeded US guidelines that were intended to protect against adverse neurodevelopmental effects. And again, as I said, most people in industrialized countries are exposed to mercury primarily through their diets in the form of methylmercury, where mercury that has traveled across the world has accumulated in those fish. And then depending on where we eat fish from, people are then exposed. And at high doses, severe damage or even death can occur, even adults. This is what happened in Minamata starting in the 1950s. But at lower doses, such as those to which many more people are exposed, those damages involve development of the nervous system, cognitive development. And it's not just pregnant women and children that have to worry about it. All adults could see impacts such as cardiovascular impacts, heart attacks, although those effects are a little bit less certain. But the health impacts of mercury depend on both the form people are exposed to and the amount of exposure. So when you think about mercury, you might be thinking about the silvery liquid. And I have an example of here. This is a droplet of mercury that's suspended in a little plexiglass pyramid. I actually bought this in an old mercury mine in Idrija, Slovenia. And people who are exposed to the elemental form could have effects, but you need a pretty high level. And people are exposed to elemental mercury at level of concern, primarily in occupational settings. For example, those gold miners who are actually using that elemental form in artisanal and small scale gold mining, and then inhale large quantities of that. Exposure to mercury vapor at elevated concentrations is quite dangerous. Some of these effects have been known for centuries. We knew that conditions in mercury mines were hazardous to workers 500 years ago. But if, for example, I broke this plexiglass container, it wouldn't be that dangerous, but I should probably open a window and dispose of it properly if that's the case. But again, the methylmercury is the form that many people are concerned about. So this elemental mercury, when it transforms and transports in the environment, will then build up as methylmercury. So thinking about the pathways of exposure is pretty complex as you think about sort of where mercury comes from, where it's going, and how people are affected. But it's also global. This is the most recent atmospheric emissions inventory for mercury. And you basically see two patterns here of emitting mercury to the atmosphere, one of which is the pattern of coal use. Coal use in China and India is quite high. Mercury emissions in the US and Europe has declined in the past several decades as a result of emissions controls. In particular, some emissions control for other air pollutants also reduce mercury emissions, and those have been implemented in several countries. But you can also see the footprint of artisanal and small-scale gold mining in the tropics, in Northern and South America, and across Africa. But there's another thing that makes mercury unique here. And one of which is, you know, if you should remember, if you took chemistry at MIT, that mercury is an element. So that means you can't get rid of it in the environment. You know, it's an elemental form. It can just change its form. And once mercury is emitted or released, it can continue to cycle for centuries or longer between the atmosphere, land, and the ocean. So this is a picture of a plate of tuna that I took, you know, back when we actually could travel. Took it in Japan, and that piece of tuna there contains a combination of naturally occurring mercury, which is really a small fraction. Mercury that's emitted recently, so today's power plants and artisanal mining that's transported across the globe built up in methyl mercury in the oceans, but also mercury emitted decades to centuries ago that continues to cycle in the environment and accumulate in fish. And the interesting thing is those historical sources stretch back centuries to millennia. The picture on the right is also one I took, is one of my last trips before the pandemic. It's from the Almudena mine in Spain, which operated for just over 2,000 years and closed in 2002, along with Idrija, Slovenia, which is where I got this droplet of mercury. It's a UNESCO World Heritage Site now, and you can go tour it. Over its history, it produced 250,000 tons of mercury, mostly mined in this form, which is cinnabar ore. It's a mercuric sulfide. And that mercury, in part, was exported to South America, where it was used in silver mining during colonial times, then potentially emitted to the atmosphere, and maybe, although there's a lot of scientific uncertainty, building up in today's tuna. And another thing about that trip was that the museum is actually in the mining hospital, and real illustration that the severe health impacts of mercury were known already hundreds of years ago. So I hope what I've convinced you from that just brief introduction to the mercury issue is how connected mercury is to some of the real things that are involved in development and human well-being over time. So people have interacted with mercury over hundreds of years, and it's really intertwined in food systems and energy systems in all sorts of ways that potentially pose lessons to how people have managed their interactions with this substance, which on the one hand, had a lot of useful properties and, for example, use in mining, but on the other hand is very dangerous and poses dangers that are different in different places. So that's really the goal of the book, is to use mercury as a really detailed, in-depth case study to look at sustainability challenges more broadly. And we do that in the book, and I'll acknowledge that my co-author is Henrik Selin at Boston University, who's an expert on international relations and some of the governance structures of mercury and global chemicals. And one of the things we do in the book is look at a couple of examples of what we call systems that mercury is characteristic of. So for example, this global cycling of mercury. Where's mercury coming from? Where is it going? It travels in the environment, but it also traveled on ships 500 years ago. How do we put that all together? Human health. So the story of Minamata. Energy industry and pollution. Mercury's connection to coal. Mercury's used in products and processes. And mercury in artisanal and small scale gold mining. And we do this by telling stories about mercury use and really trying to illustrate these connections, that mercury is not just an environmental issue, it's not just a societal issue, but it's kind of a systems issue. You can't really understand the mercury problem unless you understand not only what's going on in the environment, but things like trade, things like innovation, things like human activities, human health. So for example, we tell the story of the thermometer in chapter 6, which is about assets and liabilities. And the thermometer, the invention of the mercury thermometer was really great for science. A lot of the advances that we see in science, an accurate temperature measuring device to really understand the climate, to understand to measure chemical reactions. And today, mercury is being phased out in thermometers, but when in the history of the thermometer would you think about potentially phasing it out? Was it a mistake to use it in the thermometer in the first place? Why did people continue to use mercury and emit mercury for so long, even when these harms were known? And how can we use this millennial scale history to understand in the future how to move societies towards a more sustainable future? And the kinds of lessons in the book, and we go through this in chapters 8, 9, and 10, really boil down to it's not just about the environment, but it's also about people and technologies and institutions and knowledge. And there's stories within the book of things like innovation, community activism, regulation, a strong component of power dynamics and justice. And another thing that we do in the book is set out a framework for breaking down these issues and try to say, okay, if you're thinking about this kind of a problem, this really thorny problem that has environmental aspects, that has governance aspects, humans, power, how would I start to break that down? And so I've used the framework in the book actually in teaching at MIT. So I teach a class in the fall semester that just ended called People and the Planet. It's a required class for undergrads who are minoring in environmental sustainability. And we use that same framework to break down a whole range of different issues, from challenges of deep sea mining to looking at single-use plastics to looking at sustainability at MIT. And we've really found it a helpful framework for breaking down all of the different aspects of the issue and thinking about how to draw lessons and really how to inform action, how to inform progress towards a more sustainable future. So with that, I'm just about out of time, but I do want to say that, in addition to storytelling, one of the things we put together when the book was released was a playlist, a Spotify playlist, because one of the fun things about Mercury, even though it's really dangerous, is that it shows up a lot in popular culture, and a lot of the themes of the book are really reflected in stories, in culture, and also in songs. So we put together this playlist, which you can find, go to our website at mercurystories.org, and you can play along and listen along to some of the songs which reflect some of the themes of the chapter. So with that, I'll end and take any general questions and look forward to our discussion.
Thank you so much, Noelle. This is such a fascinating topic, and I think that's reinforced by the fact that we already have 9 questions lined up in the Q&A. I want to remind everyone, all the alumni viewers, to ask questions of our guest today using the Q&A feature in Zoom. You can also upvote questions that you'd like to hear discussed. And I want to start this by adding that one of the reasons that I'm moderating today is that I've been a toxicology journalist for about 10 years. I've written 2 books myself, which I am not particularly advertising, but I'm using to qualify myself here. Related to toxicology, one is the Poisoner's Handbook, which looks at the invention of forensic toxicology in the United States. And my more recent book, The Poison Squad, looks at contamination and additives in food and toxic substances that way. And certainly in Poisoner's Handbook, there's a whole chapter about mercury, mostly from a homicidal reference. So I found this really fascinating, and it raised one point that I'm going to mention now, and then I hope come back to after we've been able to address some of your really interesting questions here, which is that mercury is a case study of something we see with many, many dangerous elements. It's not only that we're aware of toxic qualities of different poisons and yet use them widely with mercury, but that would also be true with arsenic, that would be true with the compound formaldehyde, that would be true with asbestos. So there's something that at some point I'd like to come back to, Noelle, and have you address looking at, what this really says about who we are as a society and how we dance with these both dangerous and useful substances. So we have a couple of questions, very specific questions that I think are relevant to everyone's health, and that has to do with teeth. The use of mercury amalgam fillings and whether they're considered dangerous at this point, and why we decided to actually, with an element which has so many toxic qualities or poisonous qualities as this, just pack them into our teeth. I wonder if you can address that issue.
Sure. There's a couple of different ways in which you can kind of think about this mercury filling. And in one way, you can think about mercury's really useful qualities of, it was a really good alternative to gold fillings when it was devised at the time. And in terms of acute toxicity, Again, the same example of, if I broke this, in the form of mercury in your mouth, we're not really concerned about health impacts. There's a small number of people who are particularly sensitive, but in terms of scientific evidence of impacts, we don't really see that. But it does, one of the reasons that it's phased out is beginning to be phased out. Well, there are a few reasons, one of which is it's actually a relatively large amount of mercury, sort of overall. And if that gets out into the environment and then turns into the more toxic form methylmercury, that's problematic. So for example, when you go to the dentist's office, if they, take out a filling, put in a new one, just wash it down the drain, that's not good. It gets into waterways. And in fact, when Massachusetts mandated dental separators in dentist offices, you could actually see that concentrations in fish went down. So the environmental impacts of dental mercury is important. Also thinking about things like cremation, for example, how does the mercury in your mouth get into the environment? The other aspect is occupational exposure. So dentists themselves. So, as you're putting the mercury in and out, that's an aspect of exposure because you can then have mercury vapor, the inhalation, as opposed to the small amount you would ingest. And for you only are there once, hopefully, maybe twice, however many fillings you have, but a dentist would be doing that the entire time. So it's another example of the sort of dose response issue. In the Minamata Convention, mercury in dentistry is sort of a continued acceptable use, and because it makes dental treatment available in a broad variety of countries, particularly where it's cheaper, even in the U.S. Recently, when I was a grad student, if you had a filling, it was pretty expensive to get the non-mercury composite filling. And you can think about that example in the developing country context, where it means maybe no dental care at all.
Yeah, that's a really excellent point. And I myself hadn't considered some of the sort of cost calculations with mercury amalgam fillings. We have a question here which really has to do and probably will help inform some of the other questions that come later, the sort of nature of mercury itself. And the question is, how can a liquid as dense as mercury be so volatile and get into the air so easily? And speaking as someone who sort of followed the chemistry of mercury, although I doubt I know as much about it as you, mercury isn't only a liquid. I mean, it's a really interesting element, right? Which at certain surface temperatures and pressures can be liquid, but also is prone to bond with other materials. So it bonds with sulfur to create cinnabar in the Earth's crust. And I wonder if you can just give people a better explanation of why something that we tend to identify with this wonderful slippery elemental mercury liquid-ish form is actually used, for instance, or turns up in emissions from coal plants and things like that.
Right. So yeah, I mean, I think the key here is that mercury, because of its sort of position on the periodic table and its chemical properties, is a pretty unique substance. Again, sort of the only liquid metal at room temperature, but also does have that property that it is very volatile and exists also in the gas phase. So the question is sort of, at what concentrations? Really, everything has an equilibrium between the liquid and the gas phase. And then what, boiling point, melting point, different density kinds of properties make it particularly useful in a broad range of applications. Again, the idea that it binds to both silver and gold is actually quite useful and is the reason why it's been used extensively in mining applications. So yeah, it's a sort of its confluence of chemical properties and the ability that this is a substance that was reasonably accessible to mine, again, in the context of cinnabar, but also exists as a contaminant in coal and fossil fuels.
Right. And so what is the riskiest exposure to mercury? And I think some of that has to do with the kind of the form of mercury we're talking about. But one of the questions then goes on to say, is it more dangerous as an airborne pollutant? And is it more dangerous if you swallow it, right? Or digest it, as in, I suppose, eating mercury contaminated fish? Or, how do you kind of assess your own risk to these different routes of exposure?
That's a great question. My guess is that for most of the people on this call, their main route of exposure is going to be eating methylmercury contaminated fish. I'm guessing that most of these people on this call don't work in occupations where they're associated with mercury. Again, because in most countries, those are been phased out. And unless someone has a artisanal mining hobby, they're not going to be exposed in that way. So for people that are, for example, the most of the population at MIT, you're concerned about the form of methylmercury in fish. Again, particularly sensitive populations include pregnant women and children, but again, all adults because of some cardiovascular impacts and other potential toxic impacts that mercury has. If you're an artisanal and small-scale gold miner, you might be exposed by breathing the mercury as well with very high levels. But the levels that are in Boston, for example, or even in an urban area, aren't at levels that actually have a toxic impact.
Yes, that's a really good point. There's a number of questions asking you to address the neurotoxic nature of mercury, which is, and in particular, the famous Mad Hatters in New Jersey, among other places, and how that came about and how we eventually dealt with that.
Yeah, so I mean, that was one of the surprising things in the book. I mean, I knew a lot of the stories about these occupational exposures. For example, the Mad Hatter. We actually tell in the book that mercury was used in felting applications. It turns out that the Mad Hatter in Lewis Carroll's Alice Adventures in Wonderland, there's a little bit of a controversy of whether that's actually a based on a mercury exposed person or not, or maybe just a mad friend of his. But certainly the phrase "mad as a hatter" comes from that mercury poisoning. But what surprised me was how frequent it was and how long ago it really stretched. You see reports from the 1500s and 1600s where miners who are in mercury mines or who are using mercury in silver and gold mining. And oftentimes these were indigenous peoples, prisoners, and they had really severe impacts and often died after short stints in mines. And these impacts were well known. It was known that they were associated with mercury exposure, yet, for a long time, really nothing was done about it. So there's a really broad history. Goldsmiths, for example, in Germany, who are known to have a lot of sick days because of their use of mercury.
I just find that whole story fascinating. So I'm going to ask this question with a little bit of context. There's a number of questions about contamination of fish. Is there ever going to be a period where we might not worry about mercury contamination of fish? Are there, can't say that, specific, aside from not eating, larger, older fish that have had a lot of opportunity to store mercury, other protective measures we might take? And of course, what do we really see as the risk to pregnant women? And the context I want to put this in actually has to do with my earlier point about other toxic compounds, which is that they did some studies up at Dartmouth looking at whether pregnant women were eating enough seafood as part of a healthy diet. And the way that they were able to tell that pregnant women were just not eating seafood at all was that they were measuring for an arsenic sugar, arsenobentene. And this is an organic form of arsenic, which means it's not dangerous to us, unlike inorganic arsenic. but there was no arsenobenzene in the blood systems or urine of any of the pregnant women. It was the lack of arsenic in their systems, which led people to realize that they were not eating fish at all. So the fact is that these are really complicated systems, I think, and ones that we should acknowledge the interaction of all these different elements. But for your own perspective, and I'll ask you this personally, do you limit your exposure to fish because of mercury? And what is your advice to people in that regard?
Yeah, so there's many questions embedded in that. I think one of the things to sort of start with is to say it depends where you get your fish from. So pretty much every waterway or every state in the United States has an advisory for mercury fished out of their local waterways, ponds, lakes of high levels of methylmercury in fish. There's also fish that you buy on the commercial market, which may come from domestic waters, may come from imported from other regions. So what you're exposed to is going to be a combination depending on sort of culture, history, what kinds of diet is available to you. If you're, for example, a subsistence fisher, that might be one of your only sources of protein. And exposure is going to vary based on sort of how much fish you're eating. Again, it is really important that pregnant women and adults eat healthy fish. And that's part of why more recent scientific advice has said, or dietary advice has said, eat fish low in mercury, not don't eat high mercury fish. So that phrasing ends up being important. So for my own, actually, one of the things that that you can do if you are a mercury researcher and go to mercury conferences is oftentimes you can get your mercury tested. So what they do is they take a little piece of your hair. It's actually quite a big piece of your hair. You have to have a good amount of hair to do it. And they send it off and they tell you where you are on the thresholds. And I'm routinely just around the threshold. And I'm in the sort of general adult population. So, the concern I would have for the most part is the cardiovascular impacts and the sort of more general adult impacts. So for my particular risk benefit ratio, I try not to eat swordfish, every week. But I'm reasonably comfortable with being around that threshold, given that, I try to have a healthy diet in general. Probably from cardiovascular perspective, should give up the French fries first before the tuna. So, it's always a personal decision, but I do enjoy eating seafood. I'm from the Boston area. I like seafood. And it's something that comes in as maybe I shouldn't have too much of this, but in a similar way to other things like red meat.
Do we worry about other exposures such as old fluorescent light bulbs or meters that used to use mercury at this particular time?
So we worry about them, but we worry about them in the sense that it's a large amount of mercury in these things, and we don't want it to get out into the environment. And that's really the primary kind of risk. You do see occasionally, stories where there's just a huge amount of mercury, in a household or in a particular facility. We worry about also industrial facilities that have used mercury and dumped it, so they have a lot of waste mercury. But in the sense of, your household breaking fluorescent lamps, or even a sort of, lab at MIT that might have a lot of old equipment, you would want to make sure to dispose of it properly. But it's not something that, should be treated as like the inner sanctum of Chernobyl at this point. It's, you can go in there and clean it up with appropriate PPE.
Yes. So there is a question about coal burning plants and whether we're doing anything particular at this point. Sorry, cough. But are we doing anything in particular at this point to better regulate those emissions? And I ask in an apolitical way because my impression is that, in fact, we've rolled back some of the protective measures regarding those plants recently. So could you address sort of the modern politics of coal plant regulation and whether you think this is an issue for those in the United States at this moment.
Absolutely. So focusing on the U.S., and I can talk briefly at the end about the international regulations, the Minamata Convention regulations, but the mercury and air toxic standards in the U.S. are the primary way that mercury is regulated from power plants, particularly coal-fired power plants. One of the things to remember about mercury emissions from power plants in the U.S. is they've been declining for a couple of decades now, and they've been declining because we have other kinds of air pollution controls that also just happen to capture mercury. And there were mercury-specific regulations on some of the other airborne sources in the 90s, for example, municipal waste incinerators and medical waste incinerators and municipal waste combustors. By the time you get to the early 2000s, the largest airborne source in the US was coal-fired power plants, and under the Clean Air Act, there were proposals to regulate that source in various different ways, which were, of course, challenged legally in various different ways. And it was sort of a long saga of, regulations proposed, them getting thrown out, regulations proposed. But finally in 2013, the latest version of those standards, the mercury and air toxic standards, were finalized. And they did stick in the sense that they were implemented in about 2015. Mercury emissions, power plants have invested in mercury specific control equipments, and mercury emissions have gone down substantially in the US since then. Now, the rollback that Deborah refers to is a proposal that is now a regulation from the Trump administration that says, the underlying sort of regulatory action way back in the early 2000s that said that we should regulate mercury from coal-fired power plants, they rolled back that part of it. Now, if you don't have that, that's kind of the foundation for the mercury and air toxic standards. Right now, the mercury and air toxic standards are still in place. So, with that new regulation in place, it's possible to then take out the mercury and air toxic standards. This is not something that most utilities are actually advocating for, because they've kind of already made that investment. It's not like you can take your mercury equipment and be like, sorry, can I just return this 5 years later? You can't go back to the store and say, I want my money back. And I think the mercury and air toxic standards probably under the Biden administration will be reasonably safe in that, although there are some ongoing legal challenges that will have to be resolved in the court system. And that remains to be seen. But in the US, actually, the US has the most, because of the mercury and air toxic standards, has some of the most advanced mercury specific regulations in the world. Under the global Minamata Convention, to which the US remains a party, the regulation is that countries have to use best available technologies to control mercury emissions from new and existing coal-fired power plants, airborne sources. And there's timeframes for that, but best available technology takes into account not just the sort of the best technical solution, but also whether it's economically feasible in different countries. So that solution will vary from country to country. For example, in India and China, it might be a little bit different, although there's increasing controls on mercury for sources there as well. Deborah, I think you're still muted.
Yeah, I'm muted, sorry. All of these questions I'm asking you are from the Q&A, and I mean, they're really smart questions. It's really been a pleasure to raise them. Some of these questions, there is a question or a couple of questions that have to do with bioaccumulation. How does the body store mercury? Are there actions we can take if we think it's in our body to reduce its presence? Is there a normal cycle of metabolization? Again, referring to arsenic, arsenic metabolizes out of your body in about 2 days. Measures we can take if we feel that we are imbibing or being exposed to mercury to sort of clean that out. And there is one question that says, would our active removal of mercury from our own systems be just as good as regulating for exposures?
Okay, there's
Or
a
at
couple
least-
questions in there. On the accumulation of mercury, so mercury is sort of in between some of the really persistent toxics and your arsenic example. It lasts in the body around a couple of months. So
Okay.
you do excrete it. It's possible for people's levels to go down, and that's part of the reason that that advice for pregnant women or women who are thinking about becoming pregnant, it can be pretty effective, because you can say, okay, you should make healthier fish choices over a period of time. And again, sort of the women of childbearing age kind of advice is for that reason, because again, you know, you do have a time constant there. It's but a reasonable one. So the other part is that a lot of the effects, though, can be irreversible. So if, for example, what was seen in Minamata, if you end up with a really, really high level, some of the cognitive neurological effects can actually be irreversible. Whether it's a substitute for regulation, I think it's definitely a complement to regulation. And thinking about sort of, you know, you asked earlier, and I don't think we talked specifically about it, this time frame for recovery question. So, you know, there are a lot of time frames in the mercury problem. One of the challenges is that, so if you're thinking about, for example, a local lake, that it has fish in it that accumulates methylmercury. Again, as I said, some of that mercury is coming into the lake, which is emitted today. Some of that is historical mercury, and then there's sort of the mercury resident in the lake, and some of that's natural. Now, you can affect the mercury that's emitted today and coming to the lake. And the good news about fish is that, you know, mercury reacts pretty quickly to inputs. The methylmercury reacts pretty quickly to inputs. So that time scale can be fast, for example, for ocean fish, although, you know, a lot of fish are older in the ocean. But when I say pretty quickly, you know, years-ish, maybe decadal timescales, not the centuries that we're talking about. On the other hand, you have a weak lever, because you can only deal with that chunk that's being emitted today. The resuspension part, you don't really have any control over. So if you're going to get more decreases in the environment, you need to take a really hefty part out of that chunk in order to see that impact in fish, because there's a whole bit that you can't control. Or at least is much harder to control, because it's not coming directly out of a coal-fired power plant. It's circulating with the ocean. So I think it's really both problems at the same time, and there's certain things that are really advantageous to do at the source, but the source isn't everything. So one of the points that we make in the book is that, you know, it's not a simple solution. It's not, oh, always look at the upstream, always look at the downstream. That these two things interact and can serve different goals and be effective in different ways, and also address different populations, which is really important in dealing with environmental challenges where impacts can be disparate.
Yeah, that's a really good point about some of the complexity. Here is a engineer's question. What are the standard methodologies to measure mercury concentrations in air or water or soil? And what's the relevant sensitivity needed? Are we tracking in part per million, part per billion? Do we need to go down to the part per billion level in trying to figure out where the risks are?
Yeah, absolutely. When you're talking about mercury, and the ones I'm most familiar with is the mercury technologies in air. We actually had a site in Boston. I'm mostly a modeler. I'm pretty much all a modeler, actually, except a couple of years ago, I had the opportunity to put a mercury measurement station on the roof of a building in Boston. And we measured mercury for a year. I had an undergrad in EAPS who was working on this as part of her senior thesis. And you measure basically at the nanogram per cubic meter level for elemental mercury in the atmosphere. And it's a pretty difficult measure to make. One, because mercury has these sort of weird properties, right? So because of the funny way it acts, it sticks to things. That's never good in the laboratory setting, right? So when you're trying to measure it, you know, a lot of the measurements use atomic fluorescence, measure for the elemental mercury. That's probably for vaporized elemental mercury, the best we can do in the atmosphere. The challenge is that mercury undergoes chemical reactions in the atmosphere. It also exists as an oxidized form. One of the real big scientific puzzles is that scientists actually don't know what that oxidized form is in the atmosphere. So we know it's mercury 2+, because that's the form that mercury likes in the atmosphere. Could be HgCl2, probably HbR2. So with bromine, could be HgOH2. This hasn't been measured yet because it's a really difficult sort of thing to sort out, and because that form would be in like picograms per cubic meter level. And there's a lot of uncertainty in the reaction of that elemental mercury to the Hg2+ form, whatever it might be, as you might expect, because we can't measure the product with any decent specificity. So that's some of the science stuff that you know, in wearing my EAPS hat, think about, and how we can use models to test where those concentrations would be and what we might find out about those reactions.
So we've got a couple more really interesting questions, and then we're going to be pretty much pushing our time limit. And a number of them involve members of our listening audience who remember playing or working with the liquid form of mercury. I mean, I'm old enough to remember this myself. When I was growing up, one of our favorite things to do was to break a mercury thermometer and then play with the little silver balls and run them all over the place. And when I was researching mercury for Poisoner's Handbook, I was relieved to find out that that mercury, because of the surface tension, isn't particularly absorptive. And so when I was pushing it around with my finger wasn't necessarily in absorbing quantities of mercury. But people are wondering, you know, was that harmful that I played with that earlier? Should I worry?
Yeah, I mean, that's not the kind of thing that you would worry about from a long-term perspective. And again, you know, if you sat and sniffed mercury for a really long period of time, like if you're in a lot of these artisanal and small scale gold mining communities where there's just a ton of liquid mercury around, in, you know, Coke cans and things like that, that's a challenge. Yeah, I think the worry is that there's just so much mercury out there that once it gets released to the environment, that everyone has had this experience, that, you know, they played with it. That's a substantial quantity of mercury when you translate that into the, you know, nanograms per cubic meter in the atmosphere that are being of concern when it turns into a tiny little bit of methyl mercury that then bioaccumulates in a fish.
Right.
You want to make sure that you can capture that mercury and put it in a place where it's not allowed to do that.
And a follow-up from this also that flows through some of these questions is, well, now I'm really interested in mercury. Could I buy it?
Well, I mean, you know, from a laboratory perspective, so probably, it depends on where you are as well. So even in laboratories, for example, laboratories in Europe, it's a very seriously controlled substance. So you would need special government permission, for example, to do that. In a lot of the products that mercury has been used in, a lot of those products are being phased out. So again, thinking about, you know, thermometers, thermostats. A few years ago, you could go to Home Depot and you could buy mercury-containing thermostats that were sort of just on the shelf. Now, pretty much the dominant technology is digital. So you end up getting some of these issues. So either I'm frozen or Deborah's frozen.
Professor Celine, I can hear you just fine.
Okay, so I can't hear Deborah, so I'll just keep going on that note by saying, I think one of the challenges in the context of the Minamata Convention on Mercury has been how to phase out this mercury over time, and how to encourage people that still have some idea of wanting to use mercury. For example, there's mercury containing skin lightening creams that are very ill-advised for use, but yet exist on black markets, for example, and convincing people that no, they actually don't want to buy those things because those can be quite dangerous is pretty important. So Joe, we seem to have lost Deborah here.
We hope she'll be back, but one or two more questions here, if you can, from the audience in the Q&A tool you can open too.
Sure.
Question about mercury in water, contaminated water from Tomas.
Yes. So yeah, there's a broad range of technologies, and one of the ways I could address contamination in water is really to tell the story of what happened in Minamata, Japan. So I introduced that as a place where actually it was methyl mercury that was released directly into Minamata Bay, and so it was a poisoning incident, and it lasted for decades. And what happened was that the local government decided to clean up the bay. And the way they did that was they dredged a bunch of the contaminated sediments. They made sort of a landfill and tried to encapsulate that mercury. And you can actually go there today. And I went there for the signing of the Minamata Convention. And it's an eco park today, and you can visit the Minamata Museum. And one of the things that motivated, in part, calling our book Mercury Stories was that there are storytellers at the Minamata Museum, and they tell the story consistent with Japanese oral tradition of storytelling about their experiences with methylmercury and poisoning. And today you can actually eat seafood that is from Minamata Bay, and we did this when we visited Minamata for the signing of the Minamata Convention. It really shows that it is possible. It's really expensive. So that's one of the challenges, is that, when you actually think about cleaning up these areas, it's in a lot of cases much less expensive to control mercury at the source than to clean them up. So Deborah, you seem to be back. We were talking about cleanup for a bit.
And we're almost out of time. Sorry, I just completely got kicked off for reasons I don't understand, but I'm glad to be back. And in the last few minutes that we have, Noel, I wish that I could bring up that question that I sort of floated at the beginning, which is, mercury is a great example of our sort of human ongoing relationship with poisonous things. We're afraid of them. We use them, we kill each other with them, we are reluctant to give them up. And I'm wondering what you think your own exploration of this particular element led you to think about sort of who we are in this historical relationship with poisonous things.
Right, that's a great question. And in fact, before I worked on mercury, I said I started working with mercury about in 2002. And before I worked on mercury, I worked on persistent organic pollutants. So chemicals like DDT and PCBs, which were regulated in the Stockholm Convention, which was signed in 2001. And I think when we think about other pollutants, the story that people often tell is, well, we invented this thing, it was great, then we found out that it was dangerous, and then we phased it out. And, of course, we should learn lessons from this narrative arc of thing where, it's a wonderful new technology. People were stupid. They put it everywhere. And then, oh, no, it's killing us. And I think what the mercury story does is it really complicates that picture, right? It's not that simple, because there's differences in place. There's differences in when the knowledge got disseminated, whether that knowledge was ignored or not in different places. People knew mercury was dangerous in the 1500s in mines. Nothing happened, right? So it's not this sort of very simple story of what happens and, mistakes were made, and then, of course, we know better now. And I think that's one of the main messages in the book, is that these are really complicated issues, they involve trade-offs, and they involve trade-offs that oftentimes reinforce existing power dynamics in our society. For example, more vulnerable people, workers, others that that don't benefit from the substance and might be harmed by its use. So really teasing that out was one of the real goals, and one of the things we do at the end of the book is provide some lessons, not only for scientists who are thinking about these issues, but also for decision makers and citizens. And one of the main lessons for citizens is really to actually tell these stories, to share what experiences have been with these kinds of substances, how they're used, what goals are for well-being, for safety, what that means to different people, and to really start that dialogue. So I'm hoping to do that in part with the book.
I think that's so exciting. And I have a few closing remarks as we're almost out of time. On behalf of the Alumni Association, thank you for tuning in to this MIT Faculty Forum online broadcast, and many thanks to Professor Seeland for joining us today. That was fascinating, I want to say personally. I enjoyed every minute of it. We'll be sure to forward all questions asked via the Q&A to our speaker today, and the Alumni Office staff will keep the chat window open for discussion purposes for another 15 minutes. This broadcast will be available on the MIT Alumni Association YouTube channel within a week of today's airing. And thank you again for participating today.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.